Well, hello everyone. I thought I'd try to stream a math textbook again. Yeah, I guess I tried in the spring to read additive combinatorics on stream, but I guess it was a little too hard to read on stream. But I'm gonna try again with this math textbook. Yeah, I'm feeling a little more confident. I had a paper get accepted, and I just finished up another project, so I'm just feeling good. I feel like now I'm powerful enough to read a math textbook on stream. Yeah, so I'm going to read High Dimensional Probability by Verschijnen. Yeah, if you want to read along, you can download this book as a PDF. I have a physical copy. Highly recommend it. I should get like an Amazon affiliate link and post it. Be a math influencer. Okay, and I'm going to try to tech up the problems as we go, because this book has like a lot of problem statements in, and I'll just type them up as we go along. Let's see, let me make sure the stream is live. Alright, looks good. Yeah, there's something funny about like Twitch stream. Like when I start streaming, it doesn't like have the counter go up always, even though like it says I'm live. But it looks like we're good. Okay, let's jump in. So I was going to skip the first chapter. Some blank pages. Oh yeah, so here's the table of contents. So yeah, the first chapter is sort of just like basic probability stuff. They like talk about random variables. Some like this is like Markov's inequality and Chebyshev limit theorem. So I think this is like Demov's central limit theorem. So yeah, important stuff. But not what we're here for. We're here for the high dimensional stuff. So yeah, I'll jump to concentration probabilities. Yeah, so concentration probabilities are like you add a bunch of things together and you want to like bound the probability you're too far away from the mean. You know, like you flip 100 coins, you get 50 heads, right? Most of the time. But not exactly 50 heads, but near 50 heads. And I guess this quantifies how near and with what probability. So yeah, let's just jump to chapter 2. So I guess I have to control F. Go. Control F concentration. Okay. There we go. Yeah, this PDF viewer doesn't like support links or something, so let's see. Everyone can read that, right? Okay, so concentration of sums of independent random variables. So why concentration inequalities? Okay, so yeah, we have some random variable and we want to show that it's near the mean. Yeah, so the simplest is Chebyshev's. So I guess they say Chebyshev's earlier in corollary 1.2.5. But basically it says the probability that x minus its mean is greater than t is less than or equal to, what should it be? It should be like the variance over t. I guess we can jump to 1.2.5 to see it. Oh, squared, right. So the variance, yeah, because it's no division squared, but then t squared. Okay. Okay. So we can use Chebyshev's to bound the distance of the number of coins from the number of heads when you flip n coins from the mean. Okay, so if we toss a fair coin n times, what is the probability that we get at least 3/4 heads? Yeah, so we expect some variance around the mean. We don't expect to get exactly n over 2 heads, but we don't expect to get all heads or all tails. That would be very surprising. Okay, so what is the expectation? It's just n over 2. A coin is either heads or tails. The expectation of number of heads is n over 2. And then what is the variance? The variance is n over 4. And how can we see that? We can see that because the coins are independent, and when you have independent random variables, the variance, and you add them together, the variances add. So an individual coin toss is like 0, 1 with 50-50 probability. So the variance is 1/2 squared, because yeah, yeah, so we get n over 4 for the variance. And then what do we get for Chebyshevs? So the probability that Sn is greater than or equal to 3/4 n, we subtract n over 2 both sides because n over 2 is the expected value, and we had this is greater than or equal to n over 4. So then this is our t, and our variance is this. So we have this over this squared, so you get something 4 over n. But so this is like a pretty slow thing because it's got this n in the denominator. And what should we expect? We should expect like a much faster decay than linear in n. And the reason we should expect that is because of the central limit theorem. If you flip a bunch of coins and you like, if you flip n coins and m times and you like plot every time you get a given number of coins, it should end up looking like a bell curve because of the central limit theorem. This is like n over 2. And a bell curve isn't like 1 over n. It doesn't look like this. It doesn't have like fat tails. It's like decaying very quickly. It looks like 1 over root 2 pi e to the minus t squared over 2. I guess this is like the standard Gaussian, and this is like a Gaussian with mean n over 2 and variance this. And of course it converges to this. It'll never exactly be this because of course the Gaussian will give us some probability of like being negative, but you can always get at least 0 heads. Okay, so yeah, we can model Sn as the sum of independent random variables, and then central limit theorem implies that this normalized thing, the sum minus the mean over the variance, should be roughly equal to the standard Gaussian. And yeah, and then the standard Gaussian decays quite quickly. I guess to see that, we introduce this proposition which bounds the tails of the normal distribution. Yeah, so what I wrote down is the density of the normal distribution. But of course, what we care about isn't like the height here. What we care about is the area of everything greater than it. We care about the probability that we're greater than this level that we chose. Okay, so the tails are proportional to the height, though. This sort of makes sense in an environment where you're decaying very quickly, right? Because like this is some level, and then like here it's like half and half and half. So it's like sort of a geometric series. It's actually even better than a geometric series because it's got this square in the exponent. It's decaying super exponentially. So you should expect that it should be within a polynomial of the tail, and it is. That's what this proposition is saying. Let's see, how do we prove it? Okay, so what is an upper bound on the tail? So this is exactly the probability that g is greater than or equal to t. We just integrate the density. And okay, so what do we do here? So we replace x with t plus y. Okay, so this is just a u substitution, and then of course dx is dy, so we have the same dy, but then x squared becomes t squared plus x squared plus y squared, and then exponential split, so yeah, we just get this as equal to this. And then how do we bound it like this? So t is now a constant, so we just bring this out. And what's left behind? Oh, so we're giving an upper bound, so this is clearly less than or equal to 1. Because it's just got this negative exponent. So then we're just left with this e to the minus ty, which we're integrating. And of course we know how to integrate that. So we just get, that's where we get the 1 over t. Okay. Yeah, here they're pointing out that this thing is less than 1. Okay, and then, okay, so the lower bound is, or the upper bound is obtained. What about the lower bound? So it follows from this identity. Okay, so I see why this identity would imply the result, because we have that this is equal to this, which is greater than or equal to this, because this is less than 1. It's 1 minus something that's between 0 and 1. Or I guess minus something that's positive. I guess we have this for all t, in particular t that are greater than 1. So I think, oh yeah, this bound should be quite bad when t is between 0 and 1, but I guess it's like more of a tail bound, so that's not too important for our purposes. Yeah, I guess in particular as t goes to 0, this goes to infinity, but of course the true bound should go to 1. Or, yeah, this can never be greater than 1. It's 1/2 even, because it's symmetric. Okay, so let's see, where does this identity come from? It doesn't actually look familiar to me. So it's equal on the nose. So yeah, I wonder what we wanna do. So like my first instinct is to just like distribute this and split up on the minus, but that's clearly not going to work, because what we'll have left is like the integral from t to infinity of this, which is just this, which we kind of already know that we can only like do approximately. So somehow we need to use this whole expression, the 1 minus 3x to the minus 4. And what we should get is, okay, well, I guess something we can do is just differentiate this side and see that we get this. I guess that's how we verify such identities. But it would be a hard problem. Yeah, it would require a pretty clever substitution. Do you know how to do this one? I haven't let's see. Let's just differentiate this side and verify the identity. So d dt of 1 over t minus 1 over t cubed e to the minus t squared over 2. Okay, so product rule, I'll differentiate this first, and we'll get 1 minus 1 over t squared minus, or plus 3 over t to the 4th times e to the minus t squared. Oh, I guess it's like a telescoping thing, where we're going to like get a t squared no matter which one we differentiate, and those are just going to like cancel. So that's the first term, and then the other term will give us a. So now I'm differentiating this, so we'll have a minus t times everything. So we'll get 1. Yeah, there's our 1, which is key, and then we'll have a plus 1 over t squared. Okay, so this works out. Because these t squared things cancel and we're just left with the outer ones. Yeah. I guess if you wanted to like do it starting from here, you would like I don't know, I guess you would let u be t squared, or you would let x squared be u, and then yeah, I guess it would work out if you made the substitution, presumably, but yeah, easier to go the other way and verify the derivative. Okay, so now we have both tail bounds on the normal distribution. Okay, so returning to 2.2, we see that we should expect the probability of having at least 3/4 heads to be smaller than this. Yeah, so we should expect the coin flipping thing to be like a Gaussian. If you flip n coins and count it and normalize it correctly, it should look like a Gaussian, and then the Gaussian decays it decays like this. This is an upper bound. Okay, so right, so yeah, I guess it's 3/4 over n squared, but then okay, and then we divide by the variance. So I guess it should be like yeah, because we need to normalize the Gaussian, so you get this. Okay. Yeah, and so this argument is sort of very heuristical, because we want to be precise about the errors, but we weren't very precise about the actual central limit theorem error, and the central limit error is like not very good, and you can't make it better because, well, you can make it better at the tails, and that's I guess the subject of this chapter, the concentration inequality, but you can't make it better in the middle. And the reason you can't is because actually you're quite likely to hit 0, much more likely than you would predict with the central limit theorem. yeah, and then I guess that's what he's saying here. So the probability that you get exactly n over 2 is 2 to the minus n. So this is the probability of getting any given sequence of heads and tails, and then this is all sequences that are exactly n over 2. And we can get this using Stirling's, and he tells us to do it, so we should probably do it. I'll do it off in this margin. So yeah, Stirling's approximation. So we have n factorial is asymptotically equal to 1 over, right, not 1, just root 2 pi n. Yeah, root 2 pi n. Depending too much on the Gaussian, times n over e to the n. Okay, so if we wanted to apply this to that, so we have this is exactly equal to 2 to the minus n times n factorial, which is this expression. Oh yeah, I can copy paste. Yeah, I was working on something with my advisor, and like we needed Stirling's approximation, and then he just started whipping out the extra terms, and I guess you can like get like 2 or 3 more terms and like have like some little o of like n to the minus 3 out here or something. But definitely good enough for us. Okay, and then we have this with an n over 2, but squared now, so it'll be pi n or root pi n. N over 2e to the n over 2 all squared. Okay, and now you can see, I'm just going to start ignoring the constants, so the pi's are going to go away in this step. So I'll add a little squiggle. And so we've got root n over n, so that's where our 1 over root n comes from. And then what do we have? So then this 2 is going to cancel with this 2, so we have n to the n's, those will cancel. And so we'll have so the e's to the n's will also cancel, and we'll just be left with this 2 to the n, which will cancel this. So yeah, see that it's this. Nice. So we did it. Okay, so then yeah, the probability we get exactly 0 is 1 over root n, and then the probability that you get exactly 0 with the standard Gaussian is just 0 because it's a continuous distribution. Yeah, so the pointwise error has to be at least 1 over root n. Okay, so here we get our first exercise. Just 1 coffee cup. So I have my coffee ready. Some Honduran beans. I was thinking I would like actually tech it up. So let's try to do that. Okay, so what is this saying? It's saying that the probability. Oh, who wrote this, by the way? Oh yeah. This is Verscheinen's textbook, High Dimensional Probability. Yeah, let me post a link in the chat. I wasn't sure the best way to make it easy to follow along. I think there are ways to like make like clickable links on like the stream, right? I should probably like set that up so people can like easily download the book. Yeah, so he has like the PDF for free. But I really enjoy this book, so I guess I recommend it. Yeah, so Verscheinen wrote it. Oh yeah, and if you're watching Verscheinen, there's actually an error in the printed copy of your book. So in the online version, there's the hint right below the problem. But if in the print version, the hints are all in the back, and if you go to the back, then the hint for this is listed as 2.4.1, not 2.1.4. So you might want to fix that. Should probably let him know. He's probably not watching this stream. Okay, so I'll just write this as 2.1.4. Okay, so we want to see that the truncated squared Gaussian is exactly equal to this, and then this is less than or equal to this. Okay, so this being less than or equal to this is just the proposition, because this is less than or equal to this part of it, and this is just exactly the other part of it. So the content of the exercise is the equality. Okay, so let's see. So our goal is to compute the expectation of g squared times this indicator. I guess I should like define like probably define the indicator. Let me just do that real quick. I think this is where I have everything. Oh no, I've got it in commands. Oh hi, Cosintegrated. What are we doing? We're reading a math textbook. Let me repost the link in the chat in case you want to follow along. So yeah, we're reading High Dimensional Probability by Verschijnen, and we're doing the exercises. So yeah, right now we're trying to show that the standard normal has tails equal to this. So I guess it's commands, and I'll just define a new command. I wonder if I can just call it /1, or if LaTeX doesn't like that. Just try /1. And I think BF is the right one to do. Works. Okay, cool. Okay, so we're trying to show that this truncation is exactly equal to t times this expression. Is it for my paper? No, it's just something that we're reading this summer just for fun. It seems like very like useful to me. I guess like this first chapter and the first couple chapters are like sort of reviews, but like yeah, definitely towards the end he's talking about things that I'm not really that familiar with, but I think are very important. So yeah, just trying to expand my horizons, be more generally knowledgeable about random matrix theory. Okay, so our goal is to compute this. So what is this expectation? So the expectation, so I'll write, so where G is distributed by the standard Gaussian. You know, I didn't do zero math competitions, but it was never really my focus. I was quite bad at them. I never really like invested the time to like, I don't know, get good at them. I don't want to keep saying bath instead of math. I guess I'm looking ahead to the BF. Oh wait, no, now I can do /1. I think. Right. Okay. Yeah, I did. I guess the high point of my competitive mathematical career is I got honorary mention in the Maryland math competition. I guess UMD was hosting something. I remember it was a fun one. There was like some multiple choice thing, but then after that there was like some like Putnam style thing with like 6 questions where they got harder, and I guess I got the first one. Though they weren't even as hard as Putnam questions, of course, because they were for high schoolers. Okay, so what is the expectation? So this is equal to the integral from 0 to infinity of x times the probability that this is greater than x. /p no good? Oh right, you have to like, did I call it PR? I guess /p is already in LaTeX, unfortunately, so you can't use /p for probability. Okay, so that's the probability. Okay, so I'm going to split this up around t. So the probability that this is greater than 0 is exactly equal. So between 0 and x equals t, the probability that this is greater than t is exactly equal to the probability that g is less than t. Or is exactly... yeah, so yeah, for any x between 0 and t, we have this event if g is in fact less than t. Yeah, so we can split this up into the integral from 0 to t of x times a constant. And I guess that's where we get this term maybe. And then the rest will be, then we'll just integrate this. Okay, so what is this equal to? Okay, so this is equal to the integral from 0 to t of x times the probability that g squared is... Oh, can I explain what the expectation of g squared times... Okay, so yeah, imagine you sample like a number by the standard Gaussian. So yeah, about 0, but sometimes up to a standard deviation away, and yeah, normal Gaussian. And then if you get something that is small, so if you get something that is so this is the indicator function of what you getting being greater than t. So if what you got was large, if it was greater than t, you just return it because you multiply by 1. But if it was less than t, then you just return 0. So that's why this is called the truncated normal distribution problem. Does that make sense? Okay, so yeah, so this is now times the probability that g squared is less than or equal to, or I'll just say less than t. Yeah, I guess it's continuous. It doesn't really matter whether you write less than or less than equal. Dx. Now plus the other integral, the integral the rest of the way from 0 to, or from t to infinity of t times the probability that, or not t, x times the probability that, now g, I can just drop the indicator, g squared is greater than x, because this is the part where the indicator, yeah, so I split up into the part where the indicator is 0 and the part where the indicator is 1, essentially. So g squared is, wait, is this, right, so greater than x dx. Okay, wait, so this should not be g squared, this should just be g. Okay, and yeah, and from, so this is correct, right? So between x being 0 and t, the probability that this is greater than that value is exactly equal to the probability that this is 0, which is the complement, the probability that g is less than t. Okay. Okay, so this first one, this is now a constant, so we can just like kind of do the integral. We'll get 1/2 t squared. Should like make a command for 1/2. It's like /half. Like I type it a lot. T squared times the probability. G is less than t, which is 1 minus the probability that we care about. So hopefully this other term will cancel out nicely for us. Okay, so then we need to think about this term. So Okay, so I think we want to rewrite it instead of g squared greater than x. We want probably g greater than the square root of x. So x, probability that g is greater than the square root of x dx. And now they suggest using parts. Using parts kind of makes sense as a strategy because this probability is an integral, so we don't really know how to compute that exactly, but we do know how to compute the derivative, because the derivative of the probability being greater than something is just the density, and we know the density of the normal. It's just this. So yeah, I guess we should differentiate this and integrate this in our parts. So let me just write down the parts formula. So recall. So how do we remember the integral of u dv is equal to uv minus the integral of v du. So yeah, we want to recall that, and we also want to recall that the derivative of the density, or the derivative of the cumulative probability of the normal is just the density, which we know. So I'll just write that too. So the derivative of the probability g being greater than x is this, e to the minus x squared over 2. And I guess the last thing to remember is that the integral of x is 1/2 x squared, but I won't write that down. I should bind WW to just write. And I guess we should make this pretty. Do some aligning. Okay. So now we can apply parts. So what do we have? We have that. I guess I'll just start here or I'll rewrite down this integral. Yeah. So let's just yank that. Paste. So that equals. Okay, so now I'm going to okay, so this is my u. It's what I'm going to differentiate. So it stays the same in the next step. So we have the probability that g is. Wait. Looks a little funny. Oh, so we don't want to integrate from t. I just noticed, because if we integrate from t, yeah, this equality isn't quite right, because we want to start from where okay, so or do we want to start from t? Okay, so I guess I'm splitting. If I split up at x equals t, wait, what am I saying? So I want this to show up as my my u here, and then I differentiate it and have that. Is this right? Okay, so we've got u dv. I'm going to differentiate this to get this. And I guess I also need the chain rule. But if I just plug in, I don't want the probability that g is greater than the square root of t. That looks funny. Oh, okay, so I guess actually the split here shouldn't be t, it should be t squared. And then like the probability that this I feel like maybe I wanted to take the square root in the first step. So like this being greater than x is the same as the square root of this being greater than the square root of x. And then the probability that this is greater than the square root of x is still equal to this. What's the problem? Yeah, I guess it should split at t squared for x, because yeah, x up to t squared. Yeah, so until g squared is greater than t squared, this indicator will give 0. So this should be g. So this should be g less than t, but we should be integrating up to t squared. Then we get like a t to the fourth. That looks funny. So that can't be right. Let's just see how it works out, I guess. Yeah, so it does look funny though. Yeah, so I split it up. I think I should split it up at t squared. And then this would be not t squared, but t to the fourth, which looks concerning. And then we pick up from t, a base of t squared. Yeah, because so if g squared is less than t squared, then g is less than t, and the whole thing will be 0. So we get this part and this part, and then I take the square root. Okay, we'll see what happens. So I don't know. This looks a little funny, but maybe it actually does cancel out in the end. Okay, so I'm gonna now use. So this should be now at t squared. And then it's correct otherwise, I think. And now we're going to integrate this this x. So okay, yeah, I guess maybe it is going to just cancel out in the end. So we integrate x, and so of course we get 1/2 x squared, and the probability stays the same, g greater than square root of x. And then I guess we need to plug in our bounds. So our bounds are now t squared to, and then we have the other part. So we still need to integrate from t squared to infinity of, okay, now we're going to integrate this, and we also have to differentiate this, and we need the chain rule. And the chain rule will be key, because then the square root is going to go in here, and we're going to get like a normal exponential, which we actually know how to integrate. I think that's how it's going to work out. But let's see. So minus the integral. So we still integrate this. X squared. And then we differentiate this. So the derivative of this is this, but then there's a chain rule bit, so we get a, so we still have the 1 over 2 pi, but then we also have 1 over 2 this, because the power rule, and then the chain rule bit. So just x over 2. Let's see how that looks. I'm doing it in a weird way, you think? Is there a... There might be a better way. Because it does sort of look like a mess here. Because here, yeah, when you try doing it by definition and the first term pops out instantly. Wait, did I make an error in the first step? This is the definition of, or I guess it's not really the definition of expectation, but like it's how I would go about integrating the expectation. You have a better way, you think? Yeah, this does look a little ugly because then we have this like x to the 3 halves. I mean, like, okay, so you integrated from t to infinity of x squared over the square root of 2 pi times e to the minus x squared over 2. I don't understand. Are you saying that's like what this is equal to? Or wait, can you do that? Don't you need to like not multiply x squared by the density of the normal? Don't you need to integrate x times the density of the normal square? I guess my point is I don't think those things are exactly equal. Are they equal? Maybe they should be. So you think in this step, like, or like, I don't know. Maybe I'm making it harder than it needs to be somehow. Okay, let me go back to the first step. Wait, so okay, so I wanted to integrate x times the density of, oh, I guess this, okay, so I wanted to multiply x times the cumulative, you can just multiply by x squared times the density, and I guess the density of g. Okay, so you, so you're saying that this integral is Oh wait, I copied the wrong thing. But so this is equal to, you think this is equal to the integral from t to infinity of x squared times the density right, so I guess if g is less than t, it contributes nothing, and then we just integrate the probability times the value. Oh yeah, I guess that works, and then we know how to. Well, we don't really know how to integrate this, but we do know that the integral is equal to this. So then you did parts with yeah. Thanks for that. Yeah, square root of 2 pi. Okay, let's try that. So this integral is equal to so the first term just pops out by itself. Okay, so we're going to differentiate this and leave this alone. Don't we get a 2? So we integral of u dv equals integral of u du. Wait, I'm not sure. Oh, there's a half here. Wait, why is there a half? Okay, so we differentiate this and leave this alone, and we get this is equal to, and I'll just plug in the t. Oh yeah, I guess because we're integrating with respect to wait, now I'm confused again. Wait, so you're saying there should be a half, and then the first term, yeah, then the first term, of course, will, when we wait, but the first term, we like, oh, there just is a half, okay. Wait, so the first term, we leave this alone, and we integrate this. Wait, don't we get a t cubed then? Or, oh no, so, okay, so we integrate this, and we wait, so is this your first step or not? Okay, so this was your first step, and then your second step was x dx goes to 1/2 dx squared. Like I'm not entirely sure I follow like what this operation means. Like, can you express in terms of a u substitution? Like, is u equal x squared? Okay. Okay, so then you end up with u, but then okay, so u equals x squared, v equals. So now you're talking about parts. Your u is x squared, and your v is whatever is left. Okay, so u stays the same, and this first bit should be like x squared times the times this integrated. Sorry. Okay. Yeah, I was actually looking at this one before. Hey. I don't know why I'm so confused. Yeah, I thought this other way was gonna work out, but then it sort of looks like weird. I guess there's like the e to the minus x, but then there's x to the 3/2. This is the wrong choice of u. Let me like try to finish the other approach to see if it was working. So this should be, so this is just going to be 1/2 t to the 4th times the probability g is greater than t. And then we, wait, this is the wrong place. Okay, and then this is the integral. So I'll just minus, so we got 1/8 pi. Oh, there should be a square root there. Is there a compiling error? Oh, right. Okay, so yeah, I'm just gonna assemble the constants. So we'll have over 4 times square root pi. And then we integrate t squared to infinity of x squared e to the, or no, x to the 3/2 e to the minus x over 2. Yeah, I guess this just must be wrong. Oh, the problem is this formula is wrong. There's no x here. What am I saying? We integrate the cumulative probability, so like this x is like implicitly already kind of there. Oh, that's why I get like these extra squares and stuff. Oh, okay. Wait, yeah, that's my problem. Where am I? Yeah, so I just delete this x, delete this x, delete this x. Okay, now when we integrate, we're integrating just a constant, so we just get exactly t squared. Oh hey, Ostjom99. I definitely need energy. Okay, so now there's none of that. It's just like the probability that g is less than t from 0, but the breakup still is t squared, so we just get a t squared times the split, and then there's no x there. Just the probability that g is greater than square root of x, and then yeah, so I guess now we use yeah, so I think we use the ideas, we use parts, but we know how to differentiate this, or yeah, so we know how to differentiate this. It's this, and we have a 1 there, so we integrate the 1 now. So there's not a 1/2 x squared, it's just x, because we're integrating 1. And in the next line, it's just t squared. And yeah, then when we integrate okay, so now we differentiate. So this should just be x. Wait. Okay, I think the first step I want to do here is actually just rewrite it as using like a u substitution. So this should be equal to the integral from t to infinity of the probability g is greater than the square root of u okay, so I'm going to let u equal the square root of x, so du equals 1 over 2 square root of x dx, which is the same thing as 2 square root of u du. Does that look right? Yeah, I still do some competitive programming. I've been sort of busy with math. I kind of wanted to read this math textbook anyway, but I guess maybe doing it on stream isn't the most efficient way to do it. But yeah, I haven't done a code forces for a while. But I should probably stick to like a core streaming thing instead of just bouncing around. But it's sort of funner. Oh wait, so now this is just the probability that g is greater than u. The whole point of this was to get rid of the square root. Right, so I let u equal the square root of x, so du equals 1 over 2 root x dx, so dx is equal to 2 root u du. Okay, and now this is just a t. No, this is just u. This is not square root of u either, because it's, yeah, okay. So, okay, everything works out now. Oh, you did the wrong substitution. You and me both, I guess. Okay, so yeah, and now we okay, so we start by differentiate. So do we differentiate this or integrate this? So I want to leave this alone, and if I leave this alone, I must. I mean, somehow it feels backwards. Like I guess it's not going to work out. But okay, so let's just try it. Okay, so I'll start by so I do know how to differentiate this, so I want it to be my u. So in the first step, I'll leave this alone, and I'll differentiate this, and I'll just get 2. Yeah, 2 times, and I'm leaving this alone, so 2 times the probability. Wait. No, I'm integrating this, so we get u squared times this. Times the probability that g is greater than, and I guess t. and then we subtract the integral from t to infinity, and now I'm going to still integrate tu, so I get a u squared, and now I differentiate this. Oh, I keep forgetting my square root. Oh, right, so I'm differentiating this, so yeah, just use the minus u squared over 2. Okay, this is negative. This one's going to be negative because it's like the bottom part. Yeah, you evaluate from, yeah, the infinity, this is the top one, and that's 0. So that's negative. And then we have the integral from t to infinity of okay, and then I guess we can integrate this by splitting up the u. So we know how to integrate u times this. So this is the same thing as u times this. So this one can be integrated. Yeah, this one can be integrated with a u substitution because we see its derivative there. And this one obviously can be differentiated. Okay. Get rid of these other lines. Okay, so let's make a u substitution with, now we integrate, yeah, we integrate this, and because we have the, and we leave this alone. So when we integrate this, we don't even pick up a, or do we pick up a 1/2? guess we should get so this one will be left alone, so we'll get u times this fraction times e to the minus u squared over 2. We have to evaluate this from t to infinity. It's not good. It's not like big. Oh, there's just too many of these. Or I guess it's amount of extra parentheses. Where though? Let's see if this compiles. Oh, it does. Okay, so the problem's in this line. Oh, that shouldn't be there. Oh, no, it should be there, but there should be a matching one. Okay. So that's the first part. And then in the second part, we subtract. So we add, okay, now we need to differentiate the u so it goes away, and we still integrate this. So we just get the integral of that du from t to infinity. Okay, and so wait, should this have been g greater than t? So why did I think it was less than t? So we're integrating the cumulative probability. The cumulative probability. Oh, the probability that you're. Wait, shouldn't it be less than? No, I'm a little confused. Because it seems like here it should be greater than. So we're integrating the cumulative starting at t squared. Okay, but it does seem like we're closing in, because now this last integral is exactly the probability. This last integral is exactly the probability that g is greater than t as desired, because we're integrating the density. No, you can post what you have. Go ahead. And this first one is exactly this. Okay, so there's still a problem because this matches up with this, but and we have this term which should cancel out with this term, but they're like not going the same way. I must have made a mistake. Okay, so I'll just copy and paste it in and see what it looks like. Okay, so this is scruffy waffle solution. Let's see what we, okay, so we integrate the density times the value starting at where we cut off. And then we okay, so we do parts where we, okay, so I don't know, maybe I'm probably just like being dumb, but I'm actually not really understanding like your notation here. Like I guess like I've never used notations like this, but I guess what you're doing is a u substitution where u is equal to like x squared or e to the minus x squared over 2. This isn't really how I think about this. Yeah, so then we are doing a parts thing where we leave x alone, and that's where this t comes from, and we okay, and so if u is equal to that, then du is equal to 2x. Okay, so that's where y, or not 2x, just x. That's why one of the x's goes away, and times e to the minus x squared over 2. Oh, but so then you have, what happens to the other? Okay, and then you integrate this to get this, and then you integrate this and differentiate this to get this. Okay, yeah, I guess I did just massively overcomplicate it. I guess in the end it worked out. I just like thought about it very differently. But I guess it's easier if you start from like this formula than this formula. Though I guess I still would like to correct this one error. So we integrate the cumulative probability, and then at t squared, so for every x between 0 and t squared, this probability is equal to the probability that g is less than t. Right? And then here we are in yeah, I guess this is like the integral, like it's like a proposition in the book. Where is it? Oh, the integral identity. Yes, this is essentially what I'm doing. 1.2.1. I keep wanting to highlight, but then I cross things out. Yeah, maybe this is just wrong. Yeah, maybe this should be a greater than here, because no, it really should be a less than, though, I think. I don't know which one of these is wrong. So clearly they should cancel out. They should be equal, but I can't figure out which one I think should be the other one. I don't know. Stupid. Yeah, so I split this up by t squared. So for any x between 0 and t squared, the probability of this, so the probability that g squared times the indicator is greater than that x is just exactly equal to the probability that, Oh, no, yeah, this should be greater than. Yeah, this should be exactly the probability that G is greater than T, because if G is greater than T, yeah, for any x between 0 and T squared, this will be 0, so less than it, unless it's all the way greater. Yeah, so this should be a greater than sign. Okay. Okay, so now we're done. Because this cancels with this, and we just got the thing they wanted. Okay, so we used the integral identity. Okay, and I guess you don't need to use the integral identity. You can just multiply like the weight times the density, and then use parts directly, or use substitution and then parts, and it's a little nicer. Okay, but both ways work out, which is good. Okay, that took a little longer than maybe it should have. Okay, but I'm glad that we have two solutions. Okay. Okay, alternatively, credit Scruffy Waffles. Scruffy Walrus. Oh, I always think you're Waffles, but of course you're Walrus. Okay. Yeah, that took a little longer than maybe it should have, but I guess I'll keep going a little bit. No, I was thinking I might actually like post my solution somewhere, so I feel like I should put credit if I'm gonna just paste your tech code into the document. Okay, so the whole point of this, what was the whole point of this? Well, I guess we just did it because it was an exercise. I don't know if it's, but I guess it's like an exercise that tells you something about the tails. Clean up this cross out. Okay, and yeah, this bound is of course trivial from the proposition. Okay, let's read a little longer. Hoeffding's inequality. Okay, yeah. So this is how we're actually going to get the exponential tail that we want, because we know that we should get one, but we can't just directly apply. We can't just directly apply the central limit theorem. It won't give us the bounds we want. Okay, so we start with a particularly simple concentration inequality which holds for sums of IID symmetric Bernoulli random variables. So symmetric Bernoulli distribution. A random variable x has symmetric Bernoulli distribution or the Rademacher distribution if it's 50-50 minus 1 plus 1. Okay, so a coin toss. Okay, and then here we get the exponential bound we want in Hoeffding's inequality. So if we have n independent symmetric Bernoulli random variables and some vector, then if we take the random sum, the probability that we're greater than t is going to be less than this exponential. Okay, yeah, so I guess this one's mean should be exactly 0. So, and I guess the probability that you're greater than 0 is going to be exactly 1/2. And then, I guess it's not exactly 1/2 because you could be 0 exactly, but it's about 1/2. And then, okay, so then if t is small, if it's small relative to the AI, then this is sort of like asking what's the probability you're greater than 0, so this doesn't give you much information, but if t is large relative to the A, then it does. Okay. So we can assume without loss of generality that the norm of the A's is 1. Okay, so why is that? So we can just divide both sides by the norm, and then dividing this whole expression by the norm is like normalizing A, and then we divided t by AI, and that's like replacing this with t over the norm and just having minus t squared over 2. So that's good. Okay, so let us recall how we deduced Chebyshev's inequality. We squared both sides and applied Markov's inequality. Let's do something similar here, but instead of squaring both sides, we multiply by a fixed parameter and exponentiate. Okay, yeah, so we multiply both sides by lambda, and now we're asking what's the probability that this is greater than this, and then Markov's inequality says that it should be equal to the expectation over t. So yeah, so we get this e to the minus lambda t, which gives a hint of how we're going to get our exponential bound times the expectation. Okay. Okay, now this, by assumption, the xi is the sum of independent random variables, so we can replace this expectation of the exponential. So the exponential, of course, splits because the exponential of a plus b is exponential a times exponential of b. So we can, and by independence, we can bring it out. So we get this other product. So now we just have to bound each of these individual things. Okay, so let us fix I. Since xi takes values -1 and +1 with probability 1/2 each, we have okay, and then this is just computing the expectation of a discrete thing. So yeah, it's 1/2 this, other half this, and there's a name for this. It's the hyperbolic cosine. And now we want to bound it in terms of one exponential. Yeah, so I guess the rationale for bounding in terms of one exponential is we want to go back to this and put them all in one exponent, but in order to do that, we need them to be in exponents individually, not the sum of exponents. So yeah, let's do this exercise as well. Oh yeah, I meant to copy and paste my, what was it, just P and S, right? I have a very optimized tech template. I haven't really used it since like my first year or something. Okay, so this is problem 2.2.3. Wait. Okay. I can't do it. I'm cooked already. Okay. So I think this one's a little easier. So I'll actually even write it out in the problem statement. So do I need to define this? No, it just already has it. Thanks, LaTeX. So the hyperbolic cosine of x is less than or equal to, or I guess I should say cosh. Okay, so we want to just compare the Taylor expansions of both sides. So let's say call, so we just want to recall that the exponent of x is equal to its Taylor expansion. So what is that? That is 1 plus x plus x over 2 I don't know if there's a better way. There might be like a more like explicit way. Like I guess just like morally speaking, this seems like it's growing very rapidly in both directions. Or I guess both are growing very rapidly, but this one has the square. So like of course asymptotically this is going to be greater, and then it's also greater at the origin. Or no, they're equal at the origin. So it must be greater everywhere, right? I guess that's an argument. I was just going to follow their hint, but I'm open to sidestepping it if you... It does seem like a lot of technology for what is at heart like a pretty almost obvious identity when you think about like the terms in it. So yeah, I guess the hyperbolic cosine then, all of the odd terms will cancel and the even terms will be equal. So it just is the it just is the even terms of this. I guess I'll write the second one. Okay, so that's the Taylor expansion of hyperbolic cosine, and then the Taylor expansion of this one is it's also only even terms because we're plugging in x squared, but then instead of the exponent being 2n factorial, it'll be n factorial over 2 to the n. So it'll be 1 plus x squared over 2 so x to the 2n over, yeah, so we get to 2 to the n, and we get n factorial. And then I guess we just have to observe that 2 to the n is less than n factorial. So we're done. Oh, I didn't put that in brackets. I sort of appreciate that LaTeX just doesn't compile if you have a straight caret. It like notices that you probably wanted math mode there. Okay, yeah, so this one's I guess a lot easier than the other one. Maybe I should prove this, but I'll leave that one to the reader. I agree, Scruffy, though, that it does seem like we're using like a lot of technology, like that, like this is equal to this for something that maybe there should be a more direct way to see. Yeah, like I don't know. Maybe it's fine just to say, oh, if this is greater than this at 0, and it's greater than this at infinity, therefore it's greater everywhere. But I don't know. It's not really a rigorous argument. Okay, so what does this show? This shows that this is less than this, yeah. Okay, and then we go back to the original product, which was here, and we've got this is less than this product, and then we can just put it in all in one exponent. That was, I guess, the whole point of making this bound at all. So we've got this. I wonder if this bound is actually like very tight between 0 and 1 or something. It probably is. Yeah, I guess it's like an equality at 0, and I imagine it actually stays pretty tight up until like yeah, I guess like until you get past 1, like these terms are like all very small, and like you get, well, I guess even this term is like actually much greater than the corresponding term here, so maybe it actually isn't that precise. I don't know. Okay, but anyway, so we've got this bound, and yeah, now so we have this for all lambda, but we want to choose the best lambda, and of course the one that makes it best is going to be the one where this equals this, which is lambda equals t over 2? Oh, just t. Yeah, just t. Oh, yeah, we don't want the lambda where this is equal to this. Yeah. I guess it's just, you just differentiate. So we differentiate with respect to lambda. We want minus t plus lambda equals 0. So lambda equals t, and we get that. Okay. And now we can apply it to coin tosses, or oh no, I guess we can't. Well, we can sort of apply it to coin tosses right away. But let's see where Rashining goes. So we can view Hoeffding's inequality as a concentration version of the central limit theorem. Indeed, the most we may expect from a concentration inequality is that the tail behaves similarly to the tail of the normal distribution. And Hoeffding's tail does exactly that. Nice. Okay. Okay, yeah, so I guess he leaves it to us to check that this is the bound we get, and I guess we should do that. Where's my pen? Okay. So let's see. So the probability that we get at least 3 over 4 n heads is equal to the probability that the sum of xi, these are plus minus 1, is greater than what? So if we have more than 3/4 n heads, then if you subtract out the 1/4, then it's n over 2, greater than or equal to n over 2. And then now we apply Hoeffding's. This should be less than or equal to exponential of t squared over 2 norm a squared. So n over 2 squared over 2. And then what is the norm of a? So they're just all 1. So the norm squared is just n. Okay, and that's why we get 8. Yeah, so we get n over 8. Okay, I checked it. Nice. Okay, so, oh yeah, and then they remark that this isn't like an asymptotic result. So we actually, oh, sorry, yeah, I should have thought about that. Yeah, so here's what I wrote. Yeah, I need to think about like where to put the camera, because I feel like I'm actually very densely using my whole screen. But I guess I don't like really need to, but I don't know. I guess there's like a lot up. Very information dense stream. Okay, yeah. So we have this inequality for everything, not just for very large n, but of course the larger n is the more interesting the bound becomes. Okay, and yeah, we can get it for two-sided ones because the negative, it's like symmetric, so the probability that the absolute value is greater than 2 is equal to this plus this, and the bounds are just like the same both sides. Oh wait, what resolution am I streaming at right now? Let's open up some stream settings. Oh wait, I have to be careful, right? I can't click stream, right? Because I guess it hides the like information that's important not to show, right? Okay, I guess I can't change it live. But yeah, I'll check it. I'll check it next time I stream. Actually, I guess for like chess streams, it probably doesn't matter. But I guess there's no reason not to stream at the highest resolution that I can, especially with my very high quality GoPro. Yeah, I could imagine how like maybe the text is like a little pixelated sometimes. Okay, yeah, I'm probably not gonna stream too much longer. I was gonna finish this section, but I guess there's a lot of problems. Maybe we can do some of them. Okay, so we get the two-sided Hoeffding's. Oh right, and then we like want to generalize Hoeffding's in a few ways. So yeah, we proved Hoeffdings for symmetric random variables, and now instead of symmetric, we just have random variables that are contained in some interval. And then they just want us to prove that the larger the intervals that they're contained in, the better bound we get. Or we know the smaller. The smaller the intervals, the better, right? Because if things are not moving around very much, then we can't get very far away from t. Like I guess in the extreme case where like mi equal, where the mi's are equal, then of course xi is a constant, and then this is a constant, and you're never going to be greater than any t greater than 0. So this will just be 0 in the extreme case. All right, so that makes sense. Let's try to prove it. I should like just insert a bunch of these. So I have them ready. Okay, so 2.2.7. Oh yeah, I can increase the size of this. Oh, what? I can't believe it increased okay. That's strange. I guess I'd increase the size and then resize it. I'll do that. Okay, so before we had really fine information about the xi, we knew exactly what they were, but now we have much weaker information. We just know that they're contained in this interval. Let's see, so we need to bound. Okay, so we still know that they're independent, and what we can follow the same argument at first, where we we exponentiate both sides, we split it up. So really the goal is just to understand the expectation of these things. So we just need to bound okay, so I guess I'll leave the xi with its mean. Right. So we've got this sum. I exponentiate both sides, and then I use the independence, and now I'm just looking at the exponential of xi minus this expectation of xi. And what I want to bound is the expectation. Okay. So, I guess like the worst case scenario is the worst case scenario should be when xi is equally balanced between little mi and big mi. I guess I'll annotate this idea. It's because I guess or maybe more like claim. Yeah, because like the more concentrated xi is, how to be precise about that though? So if we had this claim, then we'd be done, because shifting by the expectation is the same as now replacing xi with a xi, where like it's plus minus 1, and then we like can just reuse the bound we got for Rademacher random variables. So, So, I guess I just want to like concentrate the probability on like as much as I can. Like, so here we've got like little mi, we have a big mi, and it has like some probability, and here's the mean. The expectation obviously has to be between them, and then like yeah, so I guess there's some probability of being less than the expectation, and some probability of being greater than the expectation. But of course, like xi can like be maybe even continuous, and then I want to sort of argue that this is at least as concentrated as like the extreme random variable that's here and here, with equal weight. Okay, so what is this expectation? It's the integral from mi to mi of like x times the density of xi. So like probability xi equals x, but not really the density. How do you note that? Okay, but we aren't computing the expectation of x, we're computing the expectation of the exponential. So it should be like integral mi to mi of the exponential of x, and then minus the expectation. I'll call that mu. Interesting. actually getting a little tired. I think I might come back to this one. I think we can make this claim precise that this is the worst case scenario and prove it. But I don't know. I guess it's been about 2 hours. Yeah, I probably should have not spent so much time on the first problem, but we got it eventually in 2 ways. But yeah, this was sort of fun. I thought I might do this again more regularly. I feel like it's like, I don't know, fun to read out loud. Hopefully it's fun to listen. Yeah, thanks so much, Scruffy Walrus, for all your help and yeah, following along. And everyone else watching. Yeah, I'm glad you had fun. I definitely did. Yeah, I guess there's like other problems to do, but yeah, I guess we'll come back to it later. Bye, everyone.